goes. Hey, what's up guys? My name is The Cherno and welcome back to my C++ series. So today, possibly the most important episode in this entire series, we're going to talk about pointers. Now unfortunately pointers are an area that a lot of people struggle with, so I just really want to say, don't worry, don't overthink it. Pointers are actually really simple. And I also want to mention that today we'll be talking about raw pointers, not smart pointers. If you don't know what smart pointers are, don't worry about that. We'll get into that in the future. Computers deal with memory. Memory is everything to a computer. If I had to name the single most important thing in programming, it would probably be memory. When you write an application and you launch it, that entire application gets loaded into memory. All of the instructions that tell the computer what to do in the code that you've written, all of that gets loaded into memory. That's how the CPU can actually access your program and start executing its instructions. When you create a variable, when you load in data from disk, everything gets stored in memory. There is nothing you can do if you do not have memory. And pointers are extremely important for managing and manipulating that memory. So what are pointers? I'm probably going to end up saying this multiple times throughout the course of this video. A pointer is an integer, a number, which stores a memory address. That is all that it is. I don't want to get too deep into how memory actually works in a computer. I might save that for another video. But simply put, your memory inside your computer is just like one big blob. It's like one big line. That's all it is. Picture one street. If your entire city that you live in just had a single street and there was a start and there was an end, and then you had a bunch of houses. There were no houses across the road. Let's just say there's just a street and there's like a row of houses. That is what memory is in a computer. It's just a linear, one-dimensional line. And every house on that street is going to have a number, an address. So to bring that metaphor back to computers, picture that every house on that street that has an address is a byte. It is one byte of data. We obviously need a way to be able to address all of those bytes, all of those houses on our street. Because, for example, let's say someone orders something online and wants to have it delivered. It needs to be delivered into the right house. Or maybe someone's sending something. They're sending something away from their house. Either way, you need to be able to read and write from memory, from those bytes of memory from those houses. So a pointer is that address. It's the address that tells us where that house is, where that specific byte of memory is. And that's extremely important because pretty much everything we do in our code is going to be reading or writing from and to memory. Now, of course, it's perfectly possible for you in C++ to write an application that does not use pointers. You can do that. You don't necessarily need to use pointers. However, they are an extremely useful tool because, as I just mentioned, memory is probably the single most important thing you have. The single most important resource that your computer can provide to you. It's used for everything. And being able to have more control over that memory is vital. Alright, anyway. To reiterate, a pointer is just an address. It is an integer which holds a memory address. That is all that it is. Forget types, right? Types have nothing to do with any of that. Types are just some kind of fiction that we've created to make our lives easier. It doesn't matter if you have an int pointer, or maybe you have an entity class and you have an entity pointer. It doesn't matter. Types are completely meaningless, right? A pointer for all types is just that integer that holds a memory address. That's all that it is. Let's jump in and take a look at some examples. Okay, so here in Visual Studio, I've got an extremely simple project. It's just one source file. Everything that you see on the screen is the complete code that I've got written. So let's go ahead and create a pointer. We're going to create the purest of pointers because it's going to be something called a void pointer. Void basically means that it's completely typeless. Remember I said that a pointer is just an address. It's just an integer which holds an address in memory. So it doesn't need a type. If we give a pointer a type, we're just saying that the data at that address is presumed to be the type that we give it, right? It doesn't mean anything apart from that. It's just something that we can write to make our lives easier syntactically, like in the actual source code to make our lives easier, we can use types with pointers. But again, a type does not change what a pointer is. A pointer is just a memory address. It's just an integer. So a void pointer means that we do not care right now in our source code what type this actual data is because we just want to really hold an address. So let's go ahead, I'll call it PTR or pointer for short. and I'll set it equal to 0. So what is 0? We've given this pointer a memory address of 0. What does that mean? Well, 0 isn't actually a valid memory address. Memory addresses do not go all the way down to 0. 0 is invalid, and what that means is that this pointer is not valid. Being not valid is a perfectly acceptable state for a pointer, but all I'm saying here is that 0 is not a valid memory address. We can't read from or write to a memory address of 0. If we try and do that, our program will crash. So 0 means null, and we can actually also write it like this, which is actually just a hash define. If you look up what that null actually is, you can see it's just a hash define for 0. So it's the same as if we wrote 0. Or we can use a C++ keyword called null pointer. This was introduced in C++ 11. So awesome, we've made our first pointer. It is completely typeless, and it has the memory address of 0. Completely useless, but it's a pointer, and this is probably the simplest pointer you could write. Let's do something a little bit more useful. Let's create an integer. So I'm going to create a variable. I'm going to call it var, and I'm going to set it equal to 8. It's going to be an integer. Now, this is just a normal integer, but of course, every variable we create has a memory address because we need a place to store that variable. So what if I want to find out what the memory address of that variable is? So where are you in memory? I can do that by using the ampersand operator. So if I use an ampersand in front of an existing variable like this, we're essentially asking this variable, hey, what is your memory address? And then of course, we're taking the memory address of that variable, and in this case, assigning it to a new variable called pointer. And that's it. We've now got the memory address of our variable, and we're storing it in another variable, which is a pointer. I'm going to put a breakpoint on this line of code and hit F5 to run and debug my application. So right now, if I take a look at what we've got a variable. You can see if I hover my mouse over it, it has the value of 8. And if I hover my mouse over pointer, it has a slightly different value, which is presented to us in hexadecimal format, but it is, as you can see, still just a number. It's an integer. So what that pointer variable is holding now is the memory address of that var variable. And that's all it is. That number that you see there, A0FB64, that is where in memory we are storing our integer variable. And in fact, what I can do is I can grab this, I can copy it, I can hit debug, Windows, memory 1. So what this view is showing now is all of the memory inside our application. I'm going to paste in that value. I'm just going to get rid of that pointer at the beginning there. And then I'm going to hit enter. And check this out. We are taken to this memory address. We know an integer is 4 bytes of data, and look at that. It has the value 8. We're looking at our computer's memory right now, and we can see that at that memory address, we have the value 8 because we created that variable and we set its value to 8. All right, fantastic. So that's really, on a basic level, that's all there is to it. Everything else builds from this. If you know this much and you're following me and you're understanding, there's no magic behind it. That's how pointers work. A pointer is a variable which holds an address, an integer. A pointer is like any other variable. It's just that instead of holding a value such as 8, it's holding a memory address, which a memory address is also a value. It's also an integer. Now, how big that integer is, how big that pointer is, depends on a lot of things. It could be a 32-bit integer, it could be a 64-bit integer, it could be a 16-bit integer. Doesn't matter, right? The point is it is an integer, and that is all it's ever going to be. If I go back to my code here and I change this to be an int pointer, I'm not actually changing anything. If I run my application again, you'll see it's not going to be any different. If I go ahead and I copy that value, I'll copy the value, I'll paste it into my memory view, and I'll hit enter, you can see it's still set to 8. I could go back here, I could make this a completely different type, such as a double. Of course, it's going to give me an error this time because the compiler is going to warn against that. I can just cast it to a double though, doesn't matter. I'm going to run my code again. I'm going to look at the value, I'm going to copy the value, I'm going to paste it over here and get rid of all this other junk at the end. Hit enter, and look at that. It takes me to that place in memory where I'm storing my data, and there are 4 bytes there that have the value 8. Types do not matter. Types are useful for manipulation of that memory. So if I want to read and write to that memory, types can help me out because the compiler will know, for example, that an integer is supposed to be 4 bytes. So when I try and set a value there, it will set 4 bytes of memory. But ultimately, types are completely meaningless. And in future videos, we're going to take a look at that even more deeply. But for now, just don't worry about types. All right, so let's go back to having our void pointer, right? Why wouldn't you always use a void pointer? Well, suppose that I wanted to get access to my data. I've got a pointer which is pointing to that data. However, now I want to actually write to or read from that data. So that variable is holding the value 8. I want to change that. How do I change that? I know where the data is, but how do I get access to it? That's where dereferencing comes in. So we've gone from a var to a pointer to var, but how do I come back to that var? Well, you can do that by sticking an asterisk out the front of your pointer. So in other words, if I write this, I'm actually dereferencing that pointer, which means that I'm now accessing the data. I can either read from or write to that data. So I could, for example, write the value 10 in here. However, if I try and do that, you'll see that I'm actually getting an error. Why? Because we've said that this pointer is a void pointer, which means that, how is the computer possibly going to write the value 10 into a void pointer? It doesn't know what it is. Is that 10 a short, which is a 2-byte integer? Is it an int, which is a 4-byte integer? Is it a long, which is an 8-byte integer? We don't know. How many bytes of data should this write, right? We've just said it's 10, but 10 could mean anything, really. That's where types come in. We need to tell the compiler, actually, no, this is an integer, so I expect you to write 4 bytes in, please. So let's just go ahead and change this to int. And now, of course, we've told the compiler this is an integer. We've told the compiler. The compiler hasn't been like, yeah, this is correct. We've told the compiler. If we make a mistake, if we say this is actually a double, we could be in trouble. If I then output the value of var, which, as you can note, is my original variable, you'll see that the value that I get is 10. Okay, so we've successfully changed it from 8 to 10. And if we go ahead and we set another breakpoint over here and run our program, I'm going to come down here into watch and actually put in that pointer. And then I'm just going to drag the value all the way up here so that we go to that spot in memory. You'll see that at that memory we're storing 8. If I hit F10 to advance my program one line, you'll see that now it's changed to 0A. A, of course, is hexadecimal for 10. So you can see that by dereferencing a pointer and writing to it, I'm basically accessing that data. In this case, I'm writing to the data at that memory address. All right, cool. So you should now know how pointers work. That's really all there is to them. A pointer just points to a location in memory. Some people say that it points to a block of memory, although this isn't really accurate because we don't know how big that block of memory is. In this case, it's 4 bytes, sure, because we've created an integer, and an integer is 4 bytes of memory, so we do have a pointer that is pointing to essentially a block of 4 bytes. However, there's nothing in the actual pointer which says how big the memory is. When we create arrays and all that, it does kind of keep track of the size. I'm not going to talk about that. But simply put, we don't know how big the pointer is. We don't know how much data it's holding, because it's not holding data, right? A pointer is just an integer, which is a memory address. That's it. Now, so far, we've been directly creating data on the stack. If I create a variable like this, we're creating it in the stack portion of our memory. I'm going to be talking about the stack and the heap and all of that in a later video. There might be like an annotation or something on the screen if I've already made that video, so go ahead and check that out if you want more details. But what I could do is create a variable on the heap. Or in other words, I could ask our computer, hey, I want you to allocate some memory for me, and I want it to be a certain size. So what I could do for now is use a char star. Now we know that a char is 1 byte, right? So when I ask something like this, I'll call it a buffer, and I'll set it equal to a new char of size 8, what I'm really asking for is 8 bytes of memory. So this has allocated 8 bytes of memory for us and is returning a pointer to the beginning of that block of memory. I could then use a function called Mem Set, which basically fills the block of memory with data that we specify. It takes in a pointer, which is going to be the pointer to the beginning of the block of memory. It's going to take in a value such as 0, and then it's going to take in a size. So how many bytes should it fill? In this case, we know that we have 8 bytes. Let's run this program. I'm going to take this. Now you'll see that this has the memory address over here. Now you already know how memory addresses work and all that, so I'm just going to type the actual variable name buffer up here and hit enter. And you'll see that, look at this. We've got 8 bytes of memory in a row, of course, that are all set to 0 because that's what we've done with our mem set. In this case, because we use the new keyword and this data is actually heap allocated, we should also delete the data when we're done with it. And we can do that just by typing in delete. We know it's an array. We use the array operator to allocate it, so we should use the delete keyword with the array operator and then delete that buffer if we were being super nice. However, our program does finish here. Anyway, the point of this example was just, again, to reiterate that this is a pointer. We've said here that we want to allocate 8 chars. A char is 1 byte, so thus we've allocated 8 bytes, and we're storing a pointer to the beginning of that data. One more thing that I want to mention is that pointers themselves are just variables. And those pointers, those variables, are also stored in memory. That's where we can get things like double pointers or triple pointers, or basically pointers to pointers. How does all that work, right? Well, you just go down a level and you're basically just saying, I now have a pointer which points to my pointer. So I now have a variable which is storing the memory address that's pointing to another variable which is storing a memory address. Simple, right? So in this example with my buffer, I could create a double pointer, right? This means it's a pointer to a pointer. I'm going to call it PTR, and I'm going to set it equal to the memory address of buffer. So now, this is where it gets interesting. I'm just going to move this breakpoint up here because I don't want to be deleting the data just yet. Let's take a look at this slowly. This is the value of pointer. I'm going to take that, I'm going to copy it in here, right? Now you can see that over here we've got B8, F1, 02, and 00. 4 bytes. I know that this pointer is going to be 4 bytes of memory because I'm running a 32-bit application, and in a 32-bit application, a memory address is 32 bits. More on that in another video. Now, because of the endianness of this computer, it's actually in reverse order. So if I paste this in here, we actually have to rearrange it so that it says 00, 02, F1, and then B8 at the end, like that. If I hit enter, look at that. I'm taken to the memory which stores this buffer of zeros. Okay? That's it. Pointers to pointers, sorted. Right? Really simple stuff. So that's it. I could keep talking about this all day, but really I'm just going to come back to saying that pointers are just integers which store a memory address. That is all that they are. Get that into your head. I'm going to be making a lot more videos on this topic and dealing with things like pointer arithmetic and more advanced kind of pointer operations. So if you're new to this channel, feel free to subscribe. As you begin to use pointers, and as we begin to use pointers throughout this series, you'll get a lot more examples and you'll see just how powerful they are and what we can do with them. But this is the gist of how they work. Don't overthink it. They're really simple. Thanks for watching, and I hope you enjoyed this video. If you did, please hit that like button. You can also follow me on Twitter and Instagram. And if you really enjoyed this video and you want to see more videos like this, you can support me on patreon.com/thecherno. Next time, we're going to be talking about references, and I'll see you guys in the next video. Goodbye.